Hello there, and welcome to the Dreamy Ocean Channel. Perhaps the day has been long, its demands echoing in your mind, leaving you feeling weary. Allow yourself this moment to simply be. Feel your shoulders soften, letting go of any lingering tension that may cling to you. Allow your jaw to unclench, releasing any tightness, and let your brow smooth like a calm surface. Take a slow, deep breath, letting it fill you completely. Then release it gently, feeling the quiet settle deeper within you with each exhalation. Tonight, we will not chase the hurried whispers of old tales, nor linger on the surface of familiar mysteries. Instead, we will embark upon a slow, deliberate descent into the very real, scientifically explored depths of a region often spoken of in hushed tones, revealing what has truly been discovered beneath its shimmering surface, far from the clamor of public announcement. We seek not sensation, but understanding nestled in the quietude of the abyssal plain. Let your mind drift now like a gentle current into the vast, serene ocean below. The ocean's quiet embrace. Defining a region of inquiry. The vast, shimmering expanse of the Atlantic Ocean, a restless blue canvas, holds within its depths a region often spoken of in hushed tones, its popular renown born from tales that ripple across the surface. Yet beneath these surface stories lies a true geographical entity, a sprawling oceanic domain that scientists approach with quiet, methodical curiosity, defining its contours not by legend, but by the immutable markers of latitude and longitude, by the subtle shifts in the Earth's crust, and by the relentless flow of its currents. This segment of our planet, loosely delineated by the points of Florida, the island of Bermuda, and the island of Puerto Rico, spans an area of profound oceanographic diversity, a true realm of scientific inquiry that far predates any popular mystique. Let us gently draw these invisible lines, not with the hurried stroke of a cartographer, but with the slow, deliberate movement of a deep-sea explorer's gaze. One vertex of this immense triangle rests near the southeastern coast of Florida, where the warm waters of the Atlantic gently lap at ancient shores. Here, the continental shelf stretches outward, a submerged extension of the North American landmass, a relatively shallow platform bathed in sunlight, teeming with life. From this vibrant, sunlit edge, the seafloor begins its gradual, almost imperceptible descent, moving away from the familiar coastal shallows and into the deeper, cooler realms of the ocean. This transition from shelf to slope marks the initial boundary, a point where the influence of land slowly yields to the boundless embrace of the open sea. Journeying eastward across hundreds of miles of deep blue water, our second vertex emerges the isolated coral-fringed archipelago of Bermuda. These islands are not continental fragments, but rather the exposed peaks of an ancient submerged volcano, a seamount rising dramatically from the abyssal plain. Imagine a colossal, silent mountain, its base rooted thousands of meters below its summit, piercing the ocean's surface to form these emerald jewels. Bermuda's very existence speaks to the deep geological forces at play in this region, a solitary sentinel in the middle of a vast, watery expanse. Its volcanic origins a testament to processes unfolding far beneath the waves over eons. The waters surrounding Bermuda plunge rapidly to great depths, creating a stark contrast between the vibrant coral reefs near the surface and the perpetual darkness of the deep ocean just a short distance away. This geological isolation and the rapid change in bathymetry make Bermuda a fascinating point of study, a natural laboratory for understanding oceanic ecosystems and geological uplift in a mid-ocean setting. Continuing our expansive slow sweep southeastward, our gaze eventually settles upon the vibrant shores of Puerto Rico, the third and final vertex. This island, larger and more geologically complex than Bermuda, is not merely a landmass, but a dynamic part of a larger tectonic boundary. Just to its north, the seafloor plunges into the profound abyss of the Puerto Rico Trench, an oceanic chasm of staggering depth. This trench is not a mere depression. It is a scar upon the Earth's face, formed where the North American tectonic plate slowly grinds beneath the Caribbean plate. Here, the ocean floor descends to depths exceeding 8,000 meters, a realm of crushing pressure and eternal night, rivaling the heights of the tallest mountains in its vertical scale. The Puerto Rico Trench is the deepest point in the entire Atlantic Ocean, a monumental geological feature that defines the southern boundary of our region of inquiry, profoundly influencing the surrounding oceanography and geology. Thus, these three distinct geographical points, the continental margin of Florida, the volcanic pinnacle of Bermuda, and the tectonically active edge of Puerto Rico, delineate a vast triangular region of the North Atlantic. It is an area encompassing approximately 1 million square miles, though its precise boundaries remain fluid and subject to various interpretations, a testament to the arbitrary nature of human-drawn lines on a constantly moving, living ocean. Within these imagined borders, the ocean floor varies dramatically from the relatively shallow continental shelves, where sunlight penetrates readily, to the truly abyssal plains that lie thousands of meters below the surface, where light never reaches and the pressure is immense. This geographical definition, far from being a static map, describes a dynamic three-dimensional volume of water and crust. It is a region where the powerful Gulf Stream, a colossal river within the ocean, flows northward along the Florida coast, carrying warm tropical waters into colder latitudes, profoundly influencing the climate of continents far away. Its swift, deep currents interact with other, less prominent flows, creating complex eddies and gyres that constantly reshape the distribution of marine life and the movement of oceanic debris. The interplay of these currents, driven by planetary rotation, temperature gradients, and salinity differences, creates a perpetually churning environment, a vast engine of global heat and nutrient distribution. Beneath these churning surface waters, the underlying geology is equally intricate. The seafloor here is a mosaic of ancient volcanic formations, vast plains, covered by eons of accumulated sediment, and the dramatic slopes of continental margins. Far to the east, though, not directly within our delineated triangle, lies the Mid-Atlantic Ridge, a colossal underwater mountain range where new oceanic crust is continuously formed as tectonic plates slowly pull apart. The influence of this immense, slow geological engine extends westward, shaping the older crust that underlies our region of inquiry, leaving its subtle, ancient marks upon the topography of the deep. Scientists study these subtle variations in bathymetry, the detailed mapping of the ocean floor, to understand the deep history of our planet, tracing the movements of continents and the birth of ocean basins over hundreds of millions of years. The very atmosphere above this region is also a crucial component of its scientific identity. Positioned within the tropical and subtropical latitudes, it is a zone frequently traversed by powerful atmospheric systems. The trade winds, consistent and strong, sweep across the surface, driving waves and influencing surface currents. Furthermore, this region lies within what is known as Hurricane Alley, a corridor through which some of the most intense tropical storms on Earth frequently track. These colossal atmospheric vortices, swirling masses of wind and rain, exert immense forces upon the ocean's surface, creating towering waves and powerful storm surges that dramatically reshape coastlines and disturb the deep ocean for days, even weeks after their passage. Understanding these atmospheric dynamics is essential for any comprehensive scientific study of the region, as the interface between the ocean and atmosphere is a constant, powerful exchange of energy and matter. Thus, when scientists speak of this region, they do not speak of a singular monolithic entity, but rather of a complex interwoven system of oceanography, geology, and atmospheric science. It is a place where the deep past of the Earth is etched into the seafloor, where the present-day forces of currents and winds sculpt the surface, and where life adapts to an astonishing range of conditions, from sunlit reefs to the crushing, lightless abyss. Our journey begins by acknowledging this profound scientific reality, by understanding the quiet, factual embrace of the ocean in this specific, sprawling domain. Setting aside the whispers of legend to listen instead to the deeper, more resonant truths that the data quietly reveals. The true inquiry into this region commences not with what has been lost, but with the boundless richness of what has always been present, patiently awaiting discovery beneath the waves. Submerged foundations. The geological architecture of the deep. The ocean's quiet embrace, which we gently explored, extends far beyond the surface currents and atmospheric exchanges. It reaches down through the water column, eventually meeting the solid, ancient foundations of our planet itself. This submerged landscape, hidden from our direct gaze, is a geological masterpiece, sculpted over hundreds of millions of years by forces of immense power and unimaginable slowness. It is here, in this deep, silent realm, that the true architecture of the Bermuda Triangle region reveals itself not as a blank canvas, but as a complex, layered testament to Earth's dynamic history. Let us begin our slow descent, moving from the familiar continental edge of Florida, where the land gradually slips beneath the waves. Here, the continental shelf extends outwards, a broad, relatively shallow platform, like a vast, submerged terrace. This shelf is composed of sedimentary rocks, accumulated layers of sand, silt, and clay, washed down from ancient rivers and coastlines over eons. Imagine these sediments, grain by grain, settling softly, building up a gentle, sloping plain, a soft bed for countless marine creatures. This shelf is a dynamic zone, constantly reshaped by currents, by the slow, grinding action of historical ice ages, and by the relentless deposition of organic matter. As we continue our imaginary journey eastward, the gentle slope of the continental shelf gives way to a more dramatic descent, the continental slope. Here, the angle steepens, considerably, plunging thousands of meters into the abyssal depths. This is a region of immense geological transition, where the thick continental crust thins and begins to meet the denser, thinner oceanic crust. The continental slope is often carved by vast submarine canyons, colossal channels etched into the seafloor resembling canyons on land, but far grander in scale and perpetually cloaked in darkness. These canyons are believed to be formed by turbidity currents, powerful underwater avalanches of sediment-laden water that surge down the slope, eroding and transporting vast quantities of material from the shallower shelf to the deep ocean basin. Picture these immense, silent cascades of mud and sand, slowly carving their way through ancient rock, shaping the underwater topography with an enduring, unseen power. At the base of the continental slope, the gradient lessens once more, spreading out into the continental rise. This is a broad, gently sloping apron of sediment formed by the accumulation of material transported down the slope by those very turbidity currents and other deep ocean processes. It is a transition zone, a soft, undulating landscape where the last whispers of continental influence fade into the vastness of the true deep ocean. Here, the sediments are finer, settling slowly from the water column, creating soft, silty plains that stretch for hundreds of miles, a quiet blanket over the underlying bedrock. Beyond the continental rise, the sea floor flattens into the immense, seemingly featureless expanse of the abyssal plain. These are the deepest, flattest, and most extensive areas of the ocean floor, typically lying at depths between 4,000 and 6,000 meters. The abyssal plains within our region of inquiry are primarily composed of oceanic crust, formed by volcanic activity along the mid-Atlantic ridge far to the east. This crust, primarily basaltic rock, is then slowly carried westward by the process of seafloor, spreading, gradually subsiding as it cools and moves away from the ridge. Over millions of years, these vast plains become covered by a thick layer of fine sediments, tiny skeletal remains of microscopic marine organisms that have drifted down from the surface, fine clays carried by currents, and dust blown from distant continents. This slow, continuous rain of particles creates a soft, muddy seabed, often appearing smooth and unbroken, yet holding within its layers a chronological record of oceanic life and geological events spanning countless millennia. Occasionally, isolated abyssal hills gently rise from these plains, often ancient subsided volcanoes, or fault blocks their peaks, softened by millennia of sediment accumulation, like forgotten mounds in an endless dark field. Now, let us turn our attention to the striking features that punctuate this vast flatness. The island of Bermuda itself, as we noted, is a surface manifestation of a much grander submerged structure, a volcanic seamount. Imagine a colossal submarine mountain, its base rooted deep within the abyssal plain, its flanks rising thousands of meters through the water column. The core of Bermuda is composed of ancient basaltic lava flows, dark, dense volcanic rock that erupted from the Earth's mantle many millions of years ago. Scientists believe that Bermuda formed over a hotspot, a plume of superheated rock, rising from deep within the mantle, creating a stationary source of volcanism as the North American plate slowly drifted over it. As the volcanic activity ceased, the seamount began to subside, slowly sinking back into the ocean. However, before it completely disappeared, coral polyps began to colonize its summit, building upward layer upon layer, forming the extensive limestone cap that now constitutes the visible islands and their surrounding reefs. This geological history explains why Bermuda is so isolated and why its deep surroundings plunge so dramatically, a solitary peak in a vast, deep basin. Southeastward, we encounter the most profound geological feature in the entire Atlantic, the Puerto Rico Trench. This immense chasm is not merely a deep hole, but a fundamental boundary where Earth's tectonic plates engage in a slow, relentless collision. Here, the North American plate, carrying the vast expanse of the Western Atlantic sea floor, is slowly, imperceptibly being forced beneath the Caribbean plate, a process known as subduction. This is a zone of immense geological stress and activity. The trench itself is a long, narrow depression extending for over 800 kilometers, 500 miles, and reaching a maximum depth of approximately 8,376 meters, 27,480 feet at the Milwaukee Deep. To put this in perspective, if Mount Everest were placed at the bottom of the Milwaukee Deep, its summit would still be more than 2,000 meters, 6,500 feet below the ocean's surface. The walls of the Puerto Rico Trench are incredibly steep, sculpted by the grinding and bending of the oceanic crust. Scientists have found unique rock types here, such as serpentinites, which are formed when mantle rocks are brought to the surface and chemically altered by seawater, a process that usually occurs deep within the Earth. The subduction process is not smooth. It occurs in fits and starts, accumulating stress that is periodically released as earthquakes. The Puerto Rico Trench region is one of the most seismically active areas in the Atlantic, with frequent tremors occurring deep beneath the ocean floor. While most of these are minor, the potential for larger earthquakes and the subsequent generation of tsunamis is a constant focus of scientific monitoring and research. The sheer scale and dynamic nature of the Puerto Rico Trench underscore the immense, powerful forces that continuously reshape our planet's crust, making it a critical area for understanding plate tectonics and its deep-seated impacts. Far to the east, beyond the immediate confines of our defined triangle, lies the Mid-Atlantic Ridge, a colossal underwater mountain range that snakes through the center of the Atlantic Ocean. This is a divergent plate boundary where the North American and Eurasian and African plates are slowly pulling apart. As they separate, molten rock or magma rises from the mantle, solidifies, and forms new oceanic crust, primarily basalt. This process, known as seafloor spreading, continuously creates new ocean floor. While the Mid-Atlantic Ridge itself is outside our region, the crust that underlies much of the Bermuda Triangle area was originally formed at this ridge. Over millions of years, this newly formed crust slowly moved westward, cooling and contracting, causing it to subside and become deeper, eventually forming the vast abyssal plains we discussed. The age of the oceanic crust here varies, becoming progressively older as one moves westward from the ridge, a geological timeline etched into the very bedrock of the ocean. Further evidence of this slow, relentless tectonic dance can be found in the subtle markings on the ocean floor fracture zones. These are long, linear scars, often thousands of kilometers long, that cut across the ocean basins perpendicular to the Mid-Atlantic Ridge. They represent ancient transform faults where segments of the oceanic crust slid past each other as they spread from the ridge. These zones are not always active faults today, but they leave a distinct topographic signature on the sea floor, often marked by abrupt changes in depth and linear ridges and valleys. They are like the faint, ancient lines on an old map, tracing the long-forgotten movements of the Earth's immense fractured plates. The accumulation of sedimentation across this entire region provides another layer of geological understanding. Beyond the terrigenous sediments from land, the deep ocean floor is blanketed by biogenic sediments primarily composed of the microscopic shells and skeletons of planktonic organisms. Foraminifera, tiny single-celled organisms with calcium carbonate shells, and radiolarians with intricate silica skeletons drift down after death, forming vast deposits of ooze. In warmer, shallower waters, calcareous oozes dominate, while in deeper, colder waters, where calcium carbonate dissolves more readily, siliceous oozes or red clays prevail. These layers, compressed over time, form sedimentary rocks, preserving a detailed, silent history of ocean chemistry, climate, and biological productivity. Scientists can extract long cores of these sediments like taking a slow, deep breath into the Earth's past, and read the story of millions of years in the changing composition of these fine, soft layers. In essence, the geological architecture beneath the Bermuda Triangle is a silent, enduring narrative of Earth's deep processes. From the gradual slope of the continental margin to the dramatic plunge of the Puerto Rico Trench, from the ancient volcanic heart of Bermuda to the vast sediment-laden abyssal plains, every contour, every rock, every layer of mud tells a story of immense forces unfolding over timescales that dwarf human comprehension. It is a world of slow, relentless creation and destruction, a foundation of quiet scientific secrets that underpin the very waters we sail upon. As we drift further into this understanding, let the profound depth and ancient stillness of these submerged foundations gently cradle your mind, inviting a deeper, more peaceful rest. Whispers of the currents, unveiling the ocean's invisible flow. Having gently explored the ancient, silent foundations beneath the waves, the immense geological architecture that cradles this part of the Atlantic, we now turn our attention to the ceaseless movement that flows above and around these submerged structures. For the ocean is never truly still. It is a realm of perpetual motion driven by forces both grand and subtle, a world of invisible rivers and slow, deep circulations that shape everything from global climate to the microscopic life within its waters. These are the whispers of the currents, the unseen flows that orchestrate the very pulse of the deep. The most prominent of these oceanic rivers, a colossal stream of warmth and energy, is the Gulf Stream. Imagine a vast, undulating ribbon of water hundreds of kilometers wide and many hundreds of meters deep, flowing with a power that dwarfs all terrestrial rivers combined. Its journey begins far to the south in the warm, enclosed basin of the Gulf of Mexico, where solar radiation heats the surface waters to a gentle warmth. From there, it funnels through the narrow, shallow confines of the Florida Straits, accelerating as it is squeezed between the land masses of Florida and Cuba. As it emerges into the open Atlantic, it gains momentum flowing northward along the southeastern coast of the United States, a vibrant blue artery against the darker, cooler surrounding waters. Within the region, we are exploring the Gulf Stream is not merely a distant phenomenon, it is a dominant defining force. It courses along the edge of the continental shelf, often flowing over the submerged landscape known as the Blake Plateau, a vast, gently sloping terrace extending off the coast of Georgia and Florida. Here, the current can reach speeds of several knots, its sheer volume of water carrying approximately 100 million cubic meters of water per second, a flow rate hundreds of times greater than all the world's rivers combined, creating a palpable force even in the deep. This immense thermal highway transports an astonishing amount of heat from the tropics towards the higher latitudes, a crucial component of Earth's climate system, moderating temperatures far across the Atlantic. As the Gulf Stream continues its journey northeastward, roughly parallel to the North American coastline, it eventually begins to detach from the continental margin, turning eastward into the open Atlantic, a broad, sweeping arc towards the vicinity of Bermuda. This eastward turn is influenced by the Coriolis effect, a deflective force caused by the Earth's rotation, which gently nudges moving objects, including massive ocean currents, to the right in the northern hemisphere. It is in this expansive eastward-flowing segment that the Gulf Stream often becomes less a single coherent ribbon and more a complex system of meanders and eddies. These meanders are like vast, slow-motion waves in the current, causing the stream to snake across the ocean. When these meanders become too pronounced, they can pinch off, forming immense swirling rings of water known as eddies. These eddies, some hundreds of kilometers in diameter, can persist for weeks or even months, slowly drifting through the ocean. Warm core eddies formed on the northern side of the Gulf Stream trap, warm, salty water from the current's core spinning clockwise. Conversely, cold core eddies formed on the southern side entrain cooler, fresher water from the surrounding Sargasso Sea, spinning counterclockwise. These vast, rotating water masses are critical for the transport of marine organisms' nutrients and heat, creating dynamic, ephemeral ecosystems within the larger ocean. Their presence and movement within the broader Bermuda Triangle area are a constant subject of study for oceanographers, as they represent significant energy transfers and influence local weather patterns. Beneath the surface, layers far removed from the direct influence of wind and solar heating move the profound, slow currents of the thermohaline circulation, often referred to as the global conveyor belt. Unlike the swift surface currents, these deep flows are driven not by wind, but by subtle differences in water density, which in turn are governed by temperature thermo and salinity haline. Imagine water becoming denser as it grows colder and saltier. In the frigid high-latitude regions of the North Atlantic, particularly near Greenland and the Labrador Sea, surface waters release heat to the atmosphere, becoming intensely cold. As sea ice forms, it extracts fresh water, leaving the remaining seawater even saltier and thus denser. This cold, dense water becomes so heavy that it slowly sinks, descending thousands of meters into the abyssal depths. Once at the bottom, this newly formed North Atlantic deepwater NADW begins a slow, vast journey southward, flowing along the ocean floor. It is like a colossal, invisible river creeping across the abyssal plains, following the contours of the submarine topography. This deep current eventually extends throughout the Atlantic around Antarctica and into the Indian and Pacific Oceans, a journey that can take hundreds, even thousands of years to complete a full cycle. Within the Bermuda Triangle region, this deep water mass is a silent, fundamental component of the ocean's structure. It carries oxygen to the deepest parts of the ocean, supporting life in realms of perpetual darkness, and slowly redistributes heat and nutrients across the globe. Its movement is almost imperceptible on human timescales, but its cumulative impact on Earth's climate and ocean ecosystems is immense and profound. Beyond these dominant flows, other surface currents driven by persistent global wind patterns also influence the region. The trade winds blowing steadily from the northeast across the tropical Atlantic generate the North Atlantic Equatorial Current, which feeds into the Gulf Stream system. Further north, the westerlies drive other surface movements. These wind-driven currents contribute to the formation of the North Atlantic Gyre, a vast clockwise, rotating system of currents that encompasses much of the North Atlantic. At the very heart of this immense gyre lies the Sargasso Sea, a unique calm, an often still region of the ocean characterized by its remarkably clear, deep blue waters and its distinctive floating mats of sargassum seaweed. This seaweed, unlike most others, does not attach to the seafloor, but floats freely, forming vast golden-brown rafts that provide habitat for a diverse array of marine life. The Sargasso Sea, with its relatively weak currents and deep, calm waters, is a distinctive feature within the broader context of the Bermuda Triangle, a quiet oasis surrounded by the restless motion of the gyre. Even the rhythmic pull of celestial bodies exerts its influence, though primarily in shallower coastal areas. The gravitational forces of the moon and the sun create the predictable rise and fall of the tides, and with them, localized tidal currents. While these are less significant in the vast, deep expanses of the open ocean within our region of inquiry, they can be pronounced near the continental shelves around islands like Bermuda and in passages between landmasses. These currents, though often slower than the Gulf Stream, can still generate considerable local movement of water, influencing sediment transport and the daily lives of coastal marine organisms. The interplay of these various currents, the swift, warm surface flow of the Gulf Stream, the slow, cold creep of the deep thermohaline circulation, the wind-driven gyres, and the rhythmic pulse of tides creates an intricate and dynamic environment. These currents interact profoundly with the underlying geological architecture. Seamounts and abyssal hills can deflect currents, creating localized eddies, or causing water to rise up, welling, or sink down, welling. The steep walls of the Puerto Rico Trench can channel deep currents, accelerating their flow or creating areas of stagnation. These interactions are crucial for understanding the distribution of nutrients and marine life. Upwelling brings nutrient-rich waters from the deep to the sunlit surface, fueling phytoplankton blooms the very base of the oceanic food web. Scientists study these invisible flows through a variety of sophisticated methods. Satellite altimetry measures minute changes in sea surface height, which can be translated into information about surface currents. Drifting buoys equipped with GPS and sensors are released into the currents, their paths tracked over months or years, revealing the larger patterns of circulation. Moorings anchored to the seafloor hold instruments like acoustic Doppler, current profilers, ADCPs, which use sound waves to measure water velocity at different depths. Deep-sea submersibles and remotely operated vehicles, ROVs, can also carry sensors to directly observe and measure currents in the abyssal realm. The ceaseless, often imperceptible movement of these oceanic currents is a fundamental truth of our planet. They are the arteries and veins of the ocean, distributing heat, oxygen, nutrients, and marine life across vast distances. Within the Bermuda Triangle, these whispers of the currents are not just a scientific curiosity. They are an essential part of the region's dynamic identity, a constant, powerful, yet mostly unseen force that shapes its waters, its life, and its profound, quiet secrets. As you drift deeper into slumber, imagine these vast, gentle currents flowing endlessly, carrying you softly into a peaceful, dream-filled ocean. Atmospheric veil, the sky's influence on the watery domain. As the slow, deep currents whisper their ancient stories around the submerged foundations, we now lift our gaze from the profound depths through the vast water column towards the boundless expanse above. For the ocean is not an isolated entity. It breathes in constant, intricate exchange with the atmosphere, a dynamic and often powerful interaction that shapes its surface, stirs its depths, and dictates the very rhythm of life within its watery domain. This atmospheric veil stretched above the Bermuda Triangle region is a complex tapestry of air masses, pressure systems, and formidable weather phenomena, all exerting their profound influence. Our journey through the sky's influence begins with the planet's grand atmospheric circulation, positioning this region within the broad embrace of the trade winds. These steady, persistent breezes, originating from the high-pressure zones near the horse latitudes, flow reliably from the northeast across the tropical and subtropical Atlantic. Imagine these winds as a gentle, unwavering hand, constantly stroking the ocean's surface, creating ripples that grow into waves, driving the surface currents that we have previously discussed. They are the initial sculptors of the ocean's face, their consistent push generating the North Atlantic Equatorial Current, which then feeds the mighty Gulf Stream. The trade winds also carry moisture, influencing the cloud formations and precipitation patterns that characterize this part of the world, often bringing with them scattered cumulus clouds like cotton tufts, drifting lazily across a cerulean sky. Interacting with these trade winds, particularly further north, are the westerlies, another global wind belt that generally moves from west to east. The shifting boundary between these two dominant wind patterns, often marked by the subtropical jet stream, is a zone of atmospheric convergence and divergence influencing the movement of weather systems across the broader North Atlantic. This delicate balance of prevailing winds creates a dynamic atmospheric environment where large-scale weather patterns are constantly evolving, guiding the path of storms and influencing the overall climate. A significant, often stabilizing atmospheric feature in this region is the Bermuda High, a semi-permanent anticyclone or high-pressure system that typically dominates the western North Atlantic during the warmer months. Picture an immense, slow-spinning dome of air gently pressing down on the ocean's surface, creating conditions of relative calm. Within the influence of the Bermuda high skies are often clear winds alight, and the ocean surface can appear remarkably smooth, reflecting the endless blue above like a polished mirror. However, this high-pressure system is not merely a harbinger of fair weather. It acts as a colossal steering mechanism for other atmospheric phenomena. Its clockwise circulation guides tropical disturbances, often shunting them westward towards the Caribbean and the Gulf of Mexico, or curving them northeastward into the open Atlantic away from continental land masses. The precise position and strength of the Bermuda High are critical factors in determining the tracks of tropical storms, a subtle yet powerful influence on the region's most dramatic weather events. Indeed, it is the potential for tropical cyclones known in this part of the world as hurricanes that truly defines the sky's most profound and formidable influence on the watery domain. The Bermuda Triangle lies squarely within Hurricane Alley, a corridor frequently traversed by these colossal atmospheric vortices. These storms begin as humble tropical depressions fueled by the warm, moist air rising from the sun-heated ocean surface. As this warm, humid air ascends, it cools, condenses, and releases latent heat, further fueling the convection and drawing in more air from below. This continuous cycle of rising air condensation and heat release creates a self-sustaining engine of immense power. Imagine a slow, swirling dance of clouds gradually tightening into a distinct spiral, its central eye a calm, often clear aperture surrounded by a towering, ferocious eye wall of intense thunderstorms. As a tropical storm intensifies into a hurricane, its sustained winds can reach staggering speeds, exceeding 150 miles per hour, generating oceanic waves of colossal scale. These waves, often reaching heights of 10 to 20 meters, 30 to 60 feet or more, are not mere surface ripples. They are immense moving walls of water capable of shattering ships and reshaping coastlines. The sheer energy imparted by these winds into the ocean creates a chaotic, churning surface, a terrifying spectacle of natural power. The influence of a hurricane extends far beneath the surface. The violent winds drag on the ocean, creating intense mixing of the water column. This mixing brings cooler, deeper waters to the surface, a process known as upwelling, which can temporarily cool the sea surface temperature in the wake of the storm, sometimes even diminishing the storm's own intensity. Conversely, the immense pressure drop within the eye of a hurricane can cause the sea surface to bulge upwards, creating a storm surge, a dome of water that can inundate coastal areas, causing catastrophic flooding. These storms also deposit vast quantities of fresh water in the form of torrential rain, temporarily altering the salinity of surface waters and impacting marine ecosystems. The passage of a single powerful hurricane can fundamentally alter oceanographic conditions in a region for weeks or even months, leaving a profound, lasting imprint on the physical and biological environment. Beyond these grand rotating systems, the atmosphere also manifests its power in more localized, yet still intense phenomena. Thunderstorms, often forming in the warm, unstable air of the tropics, can develop rapidly, bringing sudden downpours, lightning, and strong localized winds. These can organize into squall lines, elongated bands of thunderstorms that sweep across the ocean, presenting a sudden, violent, though usually short-lived hazard to surface vessels. The rapid descent of cold, dense air from these storms, known as downbursts or microbursts, can create localized, powerful blasts of wind that strike the ocean surface, generating sudden, chaotic waves that can be particularly dangerous for small crafts. Another subtle yet impactful atmospheric phenomenon is the formation of sea fog. When warm, moist air flows over a cooler ocean surface, the air near the water can cool to its dew point, causing water vapor to condense into tiny droplets, forming a dense, obscuring mist. This can drastically reduce visibility, creating disorienting conditions for navigation, shrouding the ocean in a thick, ethereal blanket. While not inherently violent, the sudden onset of dense fog can create a profound sense of isolation and disorientation, contributing to the challenges of traversing this expansive marine environment. The constant air-sea interaction is a fundamental exchange of energy and matter. Heat flows from the warmer ocean to the cooler atmosphere, driving atmospheric convection and influencing global weather patterns. Water vapor evaporates from the ocean's surface, replenishing atmospheric moisture and fueling cloud formation and precipitation. Gases such as oxygen and carbon dioxide are continuously exchanged across the air-sea interface, influencing both atmospheric composition and ocean chemistry. This dynamic boundary is a crucial focus for climate scientists, as it represents a primary pathway for the transfer of energy throughout the Earth system. Even larger, more distant climate phenomena exert a subtle long-term influence. Oscillations like the North Atlantic Oscillation, AO, a fluctuation in atmospheric pressure between the Icelandic low and the Azores high, can subtly shift storm tracks and influence seasonal temperature and precipitation patterns across the North Atlantic, including our region of inquiry. Similarly, the more globally distant El Niño Southern Oscillation, ENSO, while primarily impacting the Pacific, can have teleconnections that subtly alter atmospheric circulation patterns over the Atlantic, sometimes influencing hurricane activity in the region. These large-scale atmospheric patterns, though seemingly remote, form part of the grand interconnected web of Earth's climate, their subtle pulses resonating even in the far-flung waters of the Bermuda Triangle. Scientists meticulously study this atmospheric veil using a sophisticated array of instruments. Satellites orbiting high above provide a continuous sweeping view of cloud formations, temperature and wind patterns, tracking the birth and evolution of storms. Weather buoys anchored or drifting measure surface, atmospheric pressure, air temperature, and wind speed, relaying crucial real-time data from remote ocean locations. Weather balloons released regularly from land stations and ships ascend through the atmosphere carrying sensors that profile temperature, humidity, and wind at various altitudes. Radar systems detect precipitation and track the movement of storm cells, providing detailed information about their intensity and trajectory. These constant observations allow meteorologists to build increasingly accurate models, predicting the sky's often unpredictable influence on the watery domain. Thus, the sky above the Bermuda Triangle is far from a passive, empty space. It is a vibrant, dynamic realm, a constant partner in the ocean's story. From the gentle, persistent push of the trade winds to the terrifying majesty of a hurricane, from the stable calm of a high-pressure system to the sudden fury of a squall, the atmosphere is an omnipresent, powerful force, shaping the ocean's surface, stirring its depths and influencing the very nature of this fascinating region. As you drift deeper into the quietude of sleep, let the vast, soft expanse of the sky, with all its power and gentle breath, carry you into a peaceful, dream-filled slumber. Magnetic signatures. Earth's invisible field. Beneath the waves. From the dynamic embrace of the atmospheric veil with its swirling winds and towering storms, we now gently descend through an entirely different kind of invisible force, one that emanates not from the sky, but from the very heart of our planet. Beneath the restless surface of the ocean, and indeed permeating all things, lies Earth's magnetic field, a vast, unseen shield, a silent guardian and a profound shaper of our world. It is an invisible architecture, a fundamental property of our home, and within the Bermuda Triangle region, Its subtle signatures whisper tales of deep geology and ancient planetary processes. Imagine for a moment that our entire planet is encased within a colossal, ethereal bubble of magnetic energy. This field, stretching thousands of kilometers into space, is generated by the slow, majestic churn of molten iron and nickel within Earth's outer core, a process known as the geodynamo. Picture this liquid metal far beneath our feet, swirling and flowing under immense pressure and heat, creating electrical currents that in turn generate this pervasive magnetic force. It is a slow, relentless engine perpetually active, maintaining a field that protects our atmosphere from the harsh, erosive solar wind and guides the delicate needle of a compass across the globe. The magnetic field is not uniform, it possesses direction and intensity. Its lines of force emerge from the south magnetic pole, curve through space, and re-enter the Earth at the north magnetic pole. These magnetic poles are not perfectly aligned with the Earth's geographical poles, the points around which our planet spins. Instead, they slowly drift and wander over time, a subtle, continuous migration that adds a layer of complexity to navigation. For mariners and aviators, understanding the precise relationship between true north, the geographical pole, and magnetic north, where the compass needle points, is paramount. The difference between these two directions is called magnetic declination, and it varies depending on one's location on the Earth's surface. Within the Bermuda Triangle region, magnetic declination is a notable feature. Historically and even currently, there exists a line, a theoretical curve across the Earth's surface where magnetic north perfectly aligns with true north. This is known as the agonic line, and it has at various times in history passed through or very near the Bermuda Triangle area. When a ship or aircraft crosses this invisible line, its compass would point directly to true north, a momentary alignment. However, on either side of this line, the compass needle will deviate, pointing either slightly east or slightly west of true north. This deviation is not a mystery or an anomaly in itself. It is a known and predictable property of the Earth's magnetic field, meticulously accounted for on navigational charts through isogonic lines, which depict points of equal magnetic declination. Mariners and pilots are trained to use these charts, applying corrections to their compass readings to maintain an accurate course. The very existence and slow movement of this agonic line, therefore, are not supernatural occurrences, but rather a testament to the dynamic, scientifically understood nature of our planet's magnetic field. Beyond declination, another crucial aspect of the magnetic field is its inclination, or magnetic dip. This refers to the angle that the magnetic field lines make with the horizontal surface of the Earth. At the magnetic poles, the field lines are almost vertical, plunging directly into the Earth. At the magnetic equator, they are perfectly horizontal. As one travels from the equator towards the poles, the inclination angle gradually increases. Within the Bermuda Triangle, which spans a range of latitudes, the magnetic inclination is significant, causing a freely suspended compass needle, like that found in a dip needle, to tilt downwards. While a standard navigational compass is designed to compensate for this dip to remain horizontal, the underlying force is always present, a subtle pull downwards into the Earth, a constant reminder of the unseen field. Yet the Earth's magnetic field is not perfectly smooth or predictable in all places. It experiences localized variations like subtle ripples on a vast, invisible pond. These are known as magnetic anomalies, and they are of profound interest to geophysicists. Magnetic anomalies are deviations from the expected strength or direction of the Earth's main magnetic field, caused by differences in the magnetic properties of rocks in the Earth's crust. Certain rocks, particularly those rich in iron-bearing minerals like magnetite, can acquire a permanent magnetization when they cool from a molten state. This fossil magnetism acts like a tiny frozen compass, preserving the direction and strength of the Earth's magnetic field at the time of their formation. The oceanic crust beneath the Bermuda Triangle is a vast repository of such fossil magnetism. As we discussed in Chapter 2, the oceanic crust is continuously generated at the mid-Atlantic ridge, where magma rises and solidifies into basalt. As this basalt cools below a certain temperature, the Curie point the magnetic minerals within it align themselves with the prevailing direction of the Earth's magnetic field. Crucially, Earth's magnetic field has not always been oriented as it is today. Over geological timescales, it has periodically reversed its polarity, meaning the North Magnetic Pole and South Magnetic Pole have swapped places. These reversals occur irregularly, sometimes every few 100,000 years, sometimes more frequently. As new crust is continuously generated at the mid-Atlantic ridge and spreads outward, it records a chronological tape recording of these magnetic reversals. This creates a pattern of alternating stripes of normal and reversed magnetization on the ocean floor running parallel to the ridge. Imagine colossal invisible barcodes etched into the bedrock of the ocean. The crust underlying the Bermuda Triangle is relatively old, having spread westward from the mid-Atlantic ridge over many tens of millions of years. Therefore, this region contains a complex, intricate pattern of these magnetic stripes, each stripe a silent testament to a different epoch in Earth's magnetic history. These variations in magnetic intensity caused by the alternating polarities of the underlying basalt create detectable magnetic anomalies that can be measured by specialized instruments called magnetometers. Magnetometers towed behind ships or flown in aircraft are exquisitely sensitive devices designed to detect these subtle changes in the local magnetic field. As a research vessel slowly traverses the ocean's surface, its magnetometer continuously records the magnetic signature of the sea floor below. When the instrument passes over a body of rock with a stronger or weaker magnetization than its surroundings, it registers a magnetic anomaly. These anomalies are not mysterious. They are simply the geophysical fingerprint of the underlying geology. For example, the Bermuda Seamount, the ancient volcanic edifice upon which the islands of Bermuda rest, is composed of dense basaltic lavas. These rocks are highly magnetic, and therefore the area around Bermuda exhibits strong positive magnetic anomalies, where the local field strength is significantly higher than the regional average. Similarly, other submerged volcanic features such as seamounts and abyssal hills can create distinct magnetic signatures. Even the vast sediment-covered abyssal plains, while seemingly uniform, hold magnetic variations within their underlying crust, revealing the ancient seafloor spreading patterns. The Puerto Rico Trench, a zone of active subduction, also presents its own unique magnetic characteristics. The intense tectonic forces at play here deform and alter the oceanic crust, and the presence of deeper mantle rocks brought closer to the surface through faulting can contribute to complex localized magnetic anomalies. Scientists use detailed magnetic surveys of this region to better understand the subduction process, to map fault lines, and to characterize the composition of the crust and upper mantle. Beyond these large-scale geological features, more subtle magnetic anomalies can also arise from human activities. Sunken ships, particularly those constructed of iron or steel, create distinct magnetic signatures that can be detected by magnetometers. These magnetic ghosts on the seafloor can help locate shipwrecks, offering insights into maritime history and providing targets for archaeological exploration. Even lost aircraft, if they contain sufficient metallic components, can leave a magnetic trace. It is important to differentiate these scientifically understood magnetic variations from any popular misconceptions. While magnetic anomalies exist and can certainly cause a compass needle to deviate from its expected reading, they are generally not so extreme as to render navigation impossible or to cause inexplicable disappearances. Modern navigation systems relying on global positioning satellites, GPS, and inertial navigation units are not dependent on the Earth's magnetic field and are therefore unaffected by these localized anomalies. Furthermore, even traditional magnetic compasses, when used with up-to-date navigational charts that account for declination and local anomalies, remain reliable tools. Occasionally, the Earth's magnetic field can also be influenced by external forces, particularly from the Sun. Solar flares and coronal mass ejections from the Sun can send streams of charged particles towards Earth. When these particles interact with our planet's magnetosphere, they can cause geomagnetic storms leading to temporary fluctuations in the magnetic field. These storms can sometimes disrupt radio communications and in extreme cases affect compasses, but their effects are typically widespread and transient, not localized to one specific oceanic region. In essence, the Earth's magnetic field within the Bermuda Triangle is a powerful yet scientifically comprehensible force. It is a fundamental property of our planet, intricately linked to its deep interior and its dynamic geological past. The magnetic signatures beneath the waves are not whispers of mystery, but rather silent, enduring records of seafloor spreading volcanic activity and tectonic plate movements. By carefully mapping and interpreting these invisible magnetic variations, scientists unveil another layer of the deep, quiet secrets of this ocean realm, transforming perceived enigma into tangible, verifiable knowledge. As you drift further into the gentle currents of sleep, let the vast, unseen embrace of Earth's magnetic field hold you softly, a constant, silent presence beneath the dreams. Frozen fire, the unstable dance of methane hydrates. As we continue our slow, gentle descent into the ocean's profound depths past the subtle whispers of Earth's magnetic field, we encounter an extraordinary and paradoxical substance, a silent, fragile power hidden within the sediments of the deep. This is the realm of methane hydrates, a crystalline solid that resembles ordinary ice, but holds within its delicate structure a potent, trapped gas. It is often referred to as frozen fire, a descriptor that hints at its unusual nature and the immense energy it contains, patiently awaiting conditions that might unlock its hidden potential. Imagine, if you will, a molecular cage meticulously constructed from water molecules, forming a lattice-like structure. Within the hollow spaces of this cage, a single molecule of methane gas, the primary component of natural gas, is tightly imprisoned. This unique arrangement is known as a clathrate hydrate. It is not a chemical bond in the traditional sense, but rather a physical entrapment, a delicate balance held together by the specific conditions found far beneath the ocean's surface. To form and remain stable, methane hydrates require a precise combination of high pressure and low temperature. These conditions are met in abundance across vast stretches of the world's deep oceans, particularly along continental margins where thick layers of sediment accumulate. As we considered the geological architecture, we noted the continental slopes and rises that characterize parts of the Bermuda Triangle region, areas where the seafloor plunges to depths of hundreds or even thousands of meters. Here, the immense weight of the overlying water column generates the necessary high pressure. Simultaneously, the deep ocean waters far removed from the sun's warming rays remain perpetually cold, often just a few degrees above freezing, providing the low temperatures required for hydrate stability. The methane itself, The trapped gas originates from two primary sources. Much of it is biogenic, produced by the slow, silent work of microorganisms. Within the thick, organic-rich sediments that accumulate on the seafloor, bacteria slowly decompose dead marine organisms, releasing methane as a byproduct of their metabolic processes. This biogenic methane slowly migrates upwards through the sediment layers until it encounters the precise pressure-temperature window where hydrate formation can occur. Less commonly, methane can also be thermogenic, generated deep within the Earth's crust by the breakdown of organic matter under intense heat and pressure, similar to the formation of conventional oil and gas deposits. This thermogenic methane can then migrate along fault lines and fractures, eventually reaching the hydrate stability zone. Visually, methane hydrates can appear in various forms. Sometimes they are seen as clear, ice-like crystals, almost indistinguishable from regular ice, perhaps, with tiny trapped bubbles of gas dancing within. Other times they can be found as milky white, crystalline masses resembling dirty snow or slush, often mingled with sediment particles. They can form thin layers veins, or immense sprawling deposits within the seafloor sediments, sometimes cementing entire sections of the seabed into a rigid hydratoric layer. Scientists have even observed them as delicate shimmering structures like frozen stalagmites growing slowly from cold seeps on the ocean floor, where methaneric fluids slowly escape from beneath the sediments. Globally, methane hydrates represent an astonishingly vast reservoir of carbon, potentially holding more carbon than all other fossil fuel reserves combined. Their presence beneath the Bermuda Triangle, particularly along the Blake Ridge, a prominent submerged feature off the southeastern United States coast, is well documented and a significant area of scientific investigation. The Blake Ridge is a massive sediment drift where vast quantities of terrigenous and biogenic sediments have accumulated over millions of years, creating ideal conditions for biogenic methane generation and hydrate formation. Seismic surveys using sound waves to penetrate the sea floor have revealed widespread evidence of methane hydrates in this area, often identified by a characteristic reflection known as a bottom simulating reflector BSR, which marks the base of the hydrate stability zone. This BSR appears to mimic the seafloor topography, but lies beneath it, indicating a phase boundary where methane hydrate transitions to free methane gas. The dance of methane hydrates, however, is not always stable. The delicate balance that keeps the methane imprisoned can be disturbed, leading to a process known as dissociation. If the temperature of the surrounding water or sediment increases even by a few degrees, or if the pressure decreases, the hydrate structure can become unstable. When this happens, the water molecules release their grip on the methane, and the solid hydrate rapidly transforms into free methane gas and liquid water. Imagine this transformation occurring deep within the seafloor. A subtle warming of bottom waters, perhaps, due to a shift in deep ocean currents or a localized geothermal flux, could trigger this release. Or a sudden decrease in pressure, such as that caused by a massive submarine landslide that rapidly uncovers hydroteric sediments, could also initiate dissociation. When this frozen fire melts, the methane gas now freed seeks to escape. It rushes upwards through the sediment layers, forming immense plumes of bubbles that rise through the water column towards the surface. The consequences of such a large-scale dissociation event can be profound. Firstly, the rapid conversion of solid hydrate to gas can significantly weaken the seafloor sediments. The hydrate acts as a cement, binding the sediment particles together. When it dissociates, this cement dissolves, turning solid stable sediment into a slurry-like, unstable mass. This weakening can trigger catastrophic submarine landslides, where vast sections of the continental slope or rise suddenly slump downwards, displacing enormous volumes of water and sediment. These landslides can extend for many kilometers, reshaping the deep-sea landscape and creating powerful turbidity currents that scour the abyssal plains. One fascinating, though still theoretical, area of scientific discussion concerns the potential impact of massive rapid methane release on surface vessels. As methane gas, suddenly freed from its icy cage, rushes upwards through the water column, it could, in theory, create immense plumes of bubbles. These bubbles rising through the water would significantly decrease the density and buoyancy of the water directly above the release point. A vessel caught within such a colossal, churning plume might suddenly lose the support it needs to float, sinking rapidly, as if into an invisible, watery void. It is a powerful hypothesis, a subject of ongoing scientific modeling and debate, particularly within the context of explanations for historical maritime disappearances in regions known for hydrate deposits, though it remains important to stress that this is a theoretical mechanism and not a confirmed cause of any specific disappearance. Scientists continue to refine models to understand the scale and speed required for such an event to impact a large ship, and whether natural hydrate dissociation events could indeed reach such magnitudes. Beyond the immediate physical effects on the ocean and potential impact on vessels, methane is also a potent greenhouse gas, far more effective at trapping heat in the atmosphere than carbon dioxide over shorter timescales. If massive quantities of methane were to be released from relatively shallow hydrate deposits and reach the atmosphere, it could have significant implications for global climate. However, the vast majority of methane released from deep-sea hydrates is consumed by methane-oxidizing bacteria in the water column, or trapped within the sediments before it can reach the surface. Only if the release is exceptionally large or occurs in shallower waters does a significant amount of methane have the potential to escape into the atmosphere. This delicate balance between release and consumption is a critical area of ongoing climate research. Scientists employ a variety of advanced techniques to study these elusive deep-sea deposits. Seismic reflection profiling, as mentioned, is a primary tool allowing researchers to see layers within the seafloor and identify BSRs. Deep-sea drilling and coring operations allow for the direct retrieval of hydrate samples, which are carefully brought to the surface in specialized pressure chambers to prevent dissociation. Remotely operated vehicles. ROVs and submersibles can directly observe hydrate outcrops on the seafloor, deploying sensors to measure temperature, pressure, and methane concentrations in the surrounding water and sediments. Researchers also monitor the seafloor for pockmarks, circular depressions on the seabed that are believed to be formed by the episodic expulsion of gas and fluids from beneath the sediment's silent scars left by past hydrate dissociation events. The unstable dance of methane hydrates, therefore, is a profound and active geological process, occurring silently beneath the waves of the Bermuda Triangle and, indeed, oceans worldwide. It is a natural phenomenon driven by the slow, inexorable forces of geology, biology, and oceanography. Far from being a mysterious anomaly, it is a scientifically understood component of our planet's intricate systems, a colossal reservoir of energy, and a potential agent of significant change, both for the seafloor and, in extreme scenarios, for the global climate. As you drift into the tranquil depths of your own sleep, let the image of this frozen fire, delicately balanced and patiently awaiting its cue, remind you of the immense, unseen power that shape our world, inviting a deeper, more peaceful rest. Abyssal realms. Life flourishing in the perpetual night. From the delicate balance of frozen fire, the methane hydrates silently held captive within the sediments we now journey deeper, still immersing ourselves fully in the profound, lightless expanse that blankets the vast majority of our planet. This is the abyssal realm, a world of perpetual night, crushing pressure and chilling cold, where life against all odds not only endures but flourishes in forms both wondrous and alien to our surface-dwelling perceptions. Within the Bermuda Triangle region, these abyssal plains stretch for hundreds of miles, interrupted only by the majestic slopes of the Puerto Rico Trench, a truly Hadal domain. Imagine a descent slow and unhurried through thousands of meters of water. As we sink, the vibrant blues of the surface fade first to a deep sapphire, then to an inky indigo, until all trace of sunlight is utterly extinguished. Here below, approximately 1,000 meters, no photon from the sun has ever penetrated. This is the aphotic zone, a world defined by its eternal darkness. The temperature here is remarkably stable, hovering just above freezing, typically between 0 and 4 degrees Celsius. The pressure, however, increases relentlessly with every meter of descent. At a depth of 4,000 meters, the pressure exceeds 400 atmospheres, meaning every square centimeter of surface is subjected to a force equivalent to 400 kilograms. This is a pressure that would instantly crush most organisms from the surface world, yet it is the normal ambient condition for the creatures of the abyss. In this extreme environment, the very foundation of life photosynthesis, which powers nearly all ecosystems on Earth's surface, is utterly impossible. Without sunlight, there are no plants, no algae to convert solar energy into organic matter. So how does life survive, let alone thrive, in such a seemingly barren and hostile world? The answer lies in a slow, continuous rain of organic material drifting down from the sunlit waters far above. This is marine snow, a constant, gentle blizzard of dead phytoplankton, zooplankton, discarded larval casings, fecal pellets, and tiny fragments of decaying organisms, all slowly settling towards the seafloor. It is the primary food source for the abyssal ecosystem, a meager but persistent shower of sustenance providing the energy that fuels the deep. Beyond marine snow, other more sporadic but profoundly important sources of energy exist. The occasional whale fall, where the immense carcass of a deceased whale sinks to the abyssal plain, provides a sudden, colossal banquet. Such an event can sustain a specialized community of scavengers and decomposers, for decades creating a localized oasis of intense biological activity in an otherwise food-scarce environment. These whale falls are like immense sunken feast halls, attracting a succession of organisms from large scavengers that strip the flesh to bone-eating worms that slowly consume the skeleton itself. And then there are the remarkable oases of chemosynthesis, particularly relevant given our discussion of methane hydrates. In specific locations where the Earth's crust is fractured, or where geological processes release chemical-rich fluids, life finds an entirely different energy source. Cold seeps often associated with methane hydrate deposits are areas where methaneric fluids, sometimes accompanied by hydrogen sulfide, slowly seep from the seafloor. Here, specialized bacteria and archaea do not rely on sunlight. Instead, they perform chemosynthesis, converting the chemical energy stored in these compounds into organic matter, forming the base of a vibrant, unique food web. Imagine delicate white mats of bacteria shimmering like ethereal snowdrifts covering the sea floor. Around these seeps, feeding specialized mussels, clams and tube worms that can grow to astonishing sizes. Their bodies often bright red from the hemoglobin in their blood, thriving in an environment utterly toxic to most other life forms. These communities, once thought impossible, are powerful reminders of life's boundless adaptability. The organisms that inhabit these abyssal realms exhibit an astonishing array of adaptations to cope with the extreme conditions. To withstand the crushing pressure many deep-sea creatures have, bodies composed primarily of water-lacking gas-filled organs like swim bladders that would implode under the immense force. Their tissues are often gelatinous and soft, their bones delicate, allowing their bodies to simply deform under pressure rather than resisting it. Their enzymes and cellular processes are specially adapted to function optimally under high pressure, a biochemical marvel. In the perpetual darkness, visual adaptations are paramount. Many species, particularly fish and cephalopods, possess bioluminescence, the ability to produce their own light through chemical reactions. This light is not for illumination, but for a multitude of purposes: to attract prey, using glowing lures that dangle like baited fishing lines; to evade predators by flashing a sudden burst of light to startle or distract; to camouflage themselves by matching the faint, down-welling light from other bioluminescent organisms, counter-illumination; or to communicate with potential mates or rivals. Some creatures have evolved enormous tubular eyes designed to capture every last photon of bioluminescence in the sparse environment, while others have completely lost their eyes, relying instead on highly developed senses of touch, smell, and vibration. Food scarcity has driven another suite of adaptations. Many abyssal predators possess disproportionately large mouths and expandable stomachs, allowing them to swallow prey much larger than themselves, capitalizing on any rare feeding opportunity. The gulper eel, for instance, has a mouth so large it accounts for a quarter of its entire body length, capable of engulfing prey of considerable size. The viperfish, with its needle-sharp, inward-pointing teeth and a mouth that can unhinge, is another example of an ambush predator perfectly adapted to snatching whatever drifts by. Many creatures are also scavengers or detritivores, patiently sifting through the soft sediments for organic particles, or quickly descending upon larger food falls. Grenadiers, often called rat-tail fish, are common deep-sea scavengers with long, tapering bodies and specialized sensory organs to detect food. Reproduction in such a vast, sparsely populated environment presents its own unique challenges. Finding a mate in the eternal darkness can be incredibly difficult. Some species have evolved fascinating strategies, such as male parasitism, famously seen in certain species of anglerfish. The tiny male, upon finding a female, bites onto her, fusing his body to hers. His circulatory system connects with hers, and he slowly degenerates, becoming little more than a sperm-producing appendage, ensuring that the female always has a mate available. Other species are hermaphroditic, possessing both male and female reproductive organs, increasing their chances of successful reproduction when encountering another individual. Chemical signals, or pheromones, are also believed to play a crucial role in attracting mates across vast distances. The seafloor itself, the soft, muddy abyssal plain, is home to a diverse community of benthic organisms. Sea cucumbers, or holothurians, are abundant deposit feeders, slowly crawling across the seabed, ingesting vast quantities of sediment and extracting organic matter. Various species of starfish, brittle stars, and sea urchins also patrol the abyssal floor, acting as scavengers and predators. Amphipods and isopods, small crustaceans resembling terrestrial pillbugs, are crucial scavengers capable of rapidly consuming carrion. Even deep-sea corals exist here, not the colorful reef-building corals of shallow waters, but rather azeuxantholate corals that do not rely on sunlight for sustenance, instead filtering food particles from the water or deriving nutrition from chemosynthetic bacteria. These corals can form intricate, ancient structures providing habitat and shelter for other deep-sea fauna. The Puerto Rico Trench, pushing beyond the abyssal into the truly hadal zone depths greater than 6,000 meters, presents an even more extreme environment. Here, the pressure is even more immense, the cold more profound. Life here is even sparser, but astonishingly, it persists. Ultra-deep-sea amphipods resembling giant versions of their shallower cousins have been discovered along with specialized fish and other invertebrates. These creatures represent the absolute limits of life's endurance on Earth, their adaptations finely tuned to an existence on the very edge of possibility. Scientists explore these remote alien realms using incredibly sophisticated technologies. Remotely operated vehicles, ROVs, and autonomous underwater vehicles. AUVs equipped with high-definition cameras, powerful lights, robotic arms, and an array of sensors are sent down to explore the seafloor, collecting samples and recording observations in real time. Human-occupied submersibles such as the famous Alvin or the more recent Limiting Factor allows scientists to directly witness these incredible ecosystems, providing an invaluable perspective. Deep-sea trawls and benthic sleds are used to collect samples of organisms from the seafloor, while sediment corers extract samples of the seabed, revealing the layers of past life and geological history. Hydrophones listen for the subtle sounds of deep-sea life and geological activity, while advanced sonar systems map the intricate topography of the abyssal landscape. The Bermuda Triangle, with its vast abyssal plains, its deep continental slopes, and the profound chasm of the Puerto Rico Trench, is a crucial laboratory for understanding deep-sea life. It is a region where the whispers of the currents, the geological foundations, and the very chemistry of the ocean converge to create a unique suite of conditions that challenge yet ultimately foster life in its most resilient and imaginative forms. The creatures of these abyssal realms are not mere curiosities. They are living testaments to the adaptability of life itself, silent inhabitants of a world that remains largely unexplored, holding countless secrets within its perpetual night. As you drift deeper into the quietude of your own sleep, let the image of these wondrous, resilient beings flourishing in the deepest, darkest parts of our ocean fill your mind with a sense of profound peace and the boundless mystery of life. Echoes of ancient landscapes, submerged geological formations. As the profound stillness of the abyssal realms settles around us, revealing life's astonishing persistence in perpetual night, we now shift our focus from the living inhabitants to the very stage upon which they exist. For beneath the vast rolling waters, the ocean floor is not merely a flat, featureless expanse, but a complex, ancient landscape, deeply etched with the echoes of geological processes that have unfolded over unimaginable timescales. These submerged formations are silent monuments to Earth's dynamic history, each ridge, canyon, and plain, a chapter in a story written in rock and sediment, waiting to be deciphered by the patient gaze of science. Let us once more consider the continental margins that define the western edge of our region, the submerged extensions of the North American landmass. The continental shelf, once a fluctuating coastline over geological epochs, has accumulated vast layers of sediment laid down grain by grain over tens of millions of years. Imagine the slow, ceaseless work of ancient rivers carrying sands and silts from long-vanished mountains, depositing them gently onto the seabed. During periods of lower global sea level, particularly during past ice ages, much of this shelf would have been exposed land traversed by ancient rivers, perhaps even hosting early terrestrial life. The discovery of submerged river channels and ancient shorelines on these shelves is a tangible echo of a very different long-lost landscape now cradled beneath the waves. Beyond the shelf, the continental slope plunges dramatically into the depths. This steep incline is not a static feature but a zone of continuous, albeit slow, change. It is often incised by immense submarine canyons, colossal gashes in the seafloor that rival and often dwarf their terrestrial counterparts. These canyons, like the Hatteras Canyon system to the north of our precise region, but representative of similar features, can be many hundreds of kilometers long and thousands of meters deep. They are believed to be carved primarily by turbidity currents, dense, fast-moving flows of sediment-laden water, like underwater avalanches that surge down the slope. Picture these powerful, silent cascades originating from sediment stirred up on the shelf, or from submarine landslides slowly, relentlessly scouring pathways through ancient rock, transporting vast quantities of material from the shallow waters to the deep abyssal plains over millions of years. The intricate branching patterns of these canyons are true echoes of ancient erosional processes shaping the seabed with a power we rarely witness. At the base of these slopes, the continental rise spreads outwards, a vast, gently sloping apron of accumulated sediment. This rise is a testament to the slow, continuous deposition of material, a soft, undulating landscape, built up layer by layer from the debris carried down the slope. It represents the quiet settling of countless particles, a deep, soft blanket covering the older underlying oceanic crust. Each layer a faint whisper of past currents and distant landmasses. Beneath these sedimentary blankets lies the true bedrock of the deep ocean, the oceanic crust. This crust, primarily composed of dense, dark basalt, was born far to the east at the mid-Atlantic Ridge, a colossal underwater mountain range where new oceanic crust is continuously generated. The crust beneath our region of inquiry is ancient, having slowly migrated westward over tens of millions of years through the process of seafloor spreading. As this crust moved away from the ridge, it cooled and subsided, gradually sinking deeper into the mantle, forming the vast, deep abyssal plains. These plains, while appearing flat, are subtly corrugated by the echoes of their birth, ancient fracture zones, and transform faults linear scars thousands of kilometers long, running perpendicular to the mid-Atlantic Ridge. These are not merely cracks. They are monuments to past plate movements where segments of the crust slid past each other as they spread, leaving behind distinct topographic variations, subtle ridges and valleys that whisper of ancient tectonic stresses. Punctuating these vast plains are the majestic, isolated peaks of seamounts. These are submerged mountains, typically volcanic in origin, rising dramatically from the abyssal floor, but failing to reach the ocean's surface. The Bermuda seamount, which we touched upon earlier, is a prime example, its summit piercing the waves to form the islands of Bermuda. But many other seamounts exist entirely beneath the surface, silent dark sentinels in the deep. They are formed when magma erupts from volcanic hotspots or along crustal weaknesses, slowly building up colossal underwater mountains. Over millions of years, as the oceanic plate continues to move, these volcanoes drift away from their magma source, become inactive, and begin to subside, slowly sinking back into the mantle under their own immense weight. Some seamounts show even more profound echoes of ancient landscapes. These are the guyots, or flat-topped seamounts. Imagine a volcanic island that once rose above the waves, its summit exposed to the relentless, erosive power of wind and waves. Over millions of years, as the island slowly subsided, its top would have been planned flat by these forces, creating a broad, level summit. Then, as subsidence continued, it eventually sank entirely beneath the ocean's surface, preserving its flat top as a silent testament to a time when it stood proud above the waves. The discovery of ancient coral reefs and shallow water fossils on the flat tops of guyots, now thousands of meters deep, provides compelling evidence of past sea levels and the slow, inexorable movement of the ocean floor. These are truly submerged landscapes of a bygone era, frozen in time. Within the Bermuda Triangle, a particularly significant submerged formation is the Blake Plateau and its associated Blake Ridge. The Blake Plateau is an extensive, broad, and relatively flat area of the continental margin stretching eastward from the southeastern United States. It is deeper than the continental shelf, but shallower than the abyssal plain. This plateau is underlain by ancient sedimentary rocks, including limestones and dolomites, suggesting a complex history of deposition and subsidence. The Blake Ridge, a massive sediment drift, extends eastward from the plateau, formed by the slow, continuous accumulation of sediments transported by the powerful Gulf Stream and other deep ocean currents over millions of years. This colossal mound of sediment is where we find extensive deposits of methane hydrates, as discussed in the previous chapter. The very architecture of the Blake Ridge, a vast, undulating underwater hill, is an echo of ancient currents and the slow, patient work of sedimentation, a landscape shaped by invisible flows over geological epochs. And then there is the mighty Puerto Rico Trench, the deepest point in the Atlantic Ocean. This is not merely a hole, but a profound geological scar, an active boundary where the North American tectonic plate slowly, relentlessly plunges beneath the Caribbean plate. It is a dynamic, ongoing process, but the trench itself is an ancient feature, its formation beginning tens of millions of years ago. The steep, often fractured walls of the trench are composed of ancient oceanic crust, bent and contorted by immense tectonic forces. Submarine landslides are common here as the unstable slopes give way, sending vast quantities of sediment and rock tumbling into the abyss, further sculpting this already dramatic landscape. The trench is a place where ancient crust is recycled back into the Earth's mantle, a slow, majestic consumption that has been shaping this part of the ocean floor for eons, leaving its indelible mark. Beyond these grand features, even more subtle echoes of ancient landscapes exist. Carbonate platforms and banks, remnants of ancient shallow water environments where coral reefs and other calcifying organisms once thrived, can be found submerged to significant depths. These structures, often composed of limestone, speak of a time when this region experienced different sea levels or even different tectonic configurations, allowing for the growth of extensive reef systems that are now slowly sinking beneath the waves, becoming silent, fossilized landscapes in the deep. Scientists employ a suite of sophisticated tools to map and understand these ancient submerged landscapes. Multi-beam sonar systems mounted on research vessels emit sound waves that sweep across the seafloor, creating exquisitely detailed three-dimensional maps of the bathymetry. These maps reveal every ridge, valley, seamount, and canyon with astonishing precision, allowing geologists to visualize the topography of the deep as if the water were removed. Seismic reflection profiling using powerful sound waves that penetrate the seafloor allows researchers to see beneath the surface, revealing the layered structure of sediments and the underlying bedrock, much like an ultrasound for the Earth. This technique can identify buried channels, ancient fault lines, and the contours of deeply buried geological formations. Deep-sea drilling and coring operations bring up actual rock and sediment samples from these ancient landscapes, providing direct evidence of their composition age and past environmental conditions. The careful analysis of these cores, layer by layer, allows scientists to reconstruct the geological and oceanographic history of the region over vast stretches of time. In essence, the submerged geological formations beneath the Bermuda Triangle are far from a blank or mysterious canvas. They are a rich, complex archive of Earth's past, a silent library of ancient landscapes. From the sediment-laden shelves and slopes, etched with the scars of ancient rivers and turbidity currents, to the majestic seamounts and Guyot's remnants of long-vanished islands, and the profound tectonically active Puerto Rico Trench, every contour and composition tells a story. These are the deep, quiet echoes of our planet's enduring geological processes, transforming perceived enigma into tangible, verifiable knowledge. As you drift deeper into the gentle currents of sleep, let the vast, silent grandeur of these ancient submerged landscapes cradle your mind, inviting a deeper, more peaceful rest far beneath the surface of fleeting tales. Silent sentinels, the discovery and study of wreck sites. From the ancient, silent echoes of submerged landscapes, the vast geological forms that shape the deep, we now turn our attention to more recent, yet equally profound imprints upon the ocean floor. These are the wreck sites, the scattered remains of human endeavor, that have succumbed to the immense power of the sea, now resting in perpetual stillness. They lie as silent sentinels, not as mysterious voids, but as invaluable archives, each fragment a whisper of a lost moment, a data point for scientific inquiry, meticulously studied to unravel the true narratives of their demise and the enduring processes of the ocean itself. Imagine for a moment the final moments of a vessel, whether ship or aircraft, as it yields to an overwhelming force, be it a colossal wave, a mechanical failure, or a sudden dramatic event in the sky. The immediate impact, the fragmentation, the rapid descent through the water column. These are brutal, powerful forces that shape the initial configuration of a wreck site. A vessel might break apart on the surface, its debris scattering widely across the ocean before sinking. Or it might plunge largely intact, only to disintegrate upon impact with the hard seabed, or slowly buckle under the relentless, crushing pressure of the deep. The resulting debris field is rarely a single, neat pile. More often, it is a sprawling, often linear arrangement of scattered fragments, stretched by the forces of impact currents and the varying descent rates of different materials. The preservation of these silent sentinels is governed by a delicate interplay of environmental factors, each contributing to the slow, inexorable process of decay and transformation. The depth at which a wreck rests is perhaps the most critical determinant. In shallower sunlit waters where oxygen is abundant and temperatures are warmer, biological activity thrives. Wood-boring organisms like shipworms rapidly consume timber structures. Bacteria, both aerobic and anaerobic, accelerate the decomposition of organic materials and the corrosion of metals. Scavenging fish and invertebrates quickly strip away any soft tissues. In contrast, wrecks in the abyssal realm, thousands of meters deep, are often remarkably preserved. Here, the water is perpetually cold. Oxygen levels are significantly lower, and the biological activity of decomposers is greatly reduced. The crushing pressure, while destructive during the initial descent, then acts as a preservative, creating a stable anoxic environment where decay slows to a crawl. A wooden ship, for instance, might be reduced to a mere outline of stained sediment in shallow waters, but at abyssal depths its timbers could remain largely intact for centuries, even millennia. Sedimentation also plays a crucial role. A wreck that is quickly buried by soft accumulating sediments, whether from a submarine landslide, the slow rain of marine snow, or the deposits of turbidity currents, is largely protected from corrosive oxygen and biological activity. These sediments act as a gentle, suffocating blanket, preserving objects in an anoxic environment. Conversely, wrecks exposed on a bare, rocky seabed are subjected to the full force of currents and the constant attack of corrosive elements. The material composition of the vessel itself dictates its fate. Iron and steel hulls are susceptible to electrochemical corrosion, a slow, relentless process, where the metal reacts with seawater, forming rust and gradually disintegrating. This process can be accelerated by galvanic corrosion, where different metals in contact create an electrical current that speeds up decay. Wooden vessels, if not buried, are vulnerable to marine borers. Objects made of more resilient materials such as ceramics, glass gold, and certain plastics can endure for exceptionally long periods, emerging from the deep, remarkably unchanged silent witnesses to technologies and artistry of bygone eras. The ocean currents which we explored previously also sculpt the wreck site over time. Strong, persistent currents can scour away sediments exposing buried portions of a wreck, or conversely deposit new layers. They can also scatter lighter debris over vast distances, extending the footprint of a wreck site far beyond the initial impact zone, creating a challenging puzzle for researchers seeking to reconstruct the events of a loss. The movement of debris therefore becomes a form of forensic oceanography, allowing scientists to infer the direction and strength of currents at the time of the sinking and in the subsequent decades. The discovery of these silent sentinels is a methodical, patient process, often requiring sophisticated technology and meticulous analysis. It rarely involves stumbling upon a perfectly preserved object. Instead, it begins with historical research, poring over maritime archives, ship logs, insurance records, and survivor accounts to narrow down potential search areas. These historical whispers provide the initial coordinates for the scientific hunt. Once a target area is identified, the technological search begins. Side-scan sonar is a primary tool acting like an acoustic camera, emitting sound waves sideways and recording the echoes that bounce back from the seafloor. It creates high-resolution images of the seabed, revealing subtle changes in topography and identifying objects protruding from the bottom. Imagine a slow, sweeping beam of sound, painting a detailed shadow picture of the ocean floor, where a sudden angular anomaly could indicate the presence of a wreck. Multi-beam sonar systems, which map the bathymetry in intricate detail, also contribute, revealing any unusual depressions or rises that might suggest a submerged object. Magnetometers, as discussed in the previous chapter, are indispensable for detecting wrecks made of ferrous metals. Towed behind a vessel, these sensitive instruments measure minute variations in the Earth's magnetic field. A sudden spike or dip in the magnetic reading can indicate the presence of a large concentration of iron or steel, signaling a potential shipwreck or aircraft. These instruments are so sensitive they can detect objects, even if they are buried beneath layers of sediment, revealing the magnetic ghost of a lost vessel. Once a potential target is identified by sonar or magnetometer, the next phase involves visual inspection. This is typically performed by remotely operated vehicles, ROVs, or autonomous underwater vehicles. AUVs, equipped with powerful lights, high-definition cameras, and often robotic manipulator arms. These unmanned submersibles can descend to great depths, hovering over the wreck site, providing scientists with their first direct glimpse of the lost vessel. They meticulously document the site, taking thousands of photographs and video footage, creating detailed three-dimensional maps of the debris field. In rare and specialized cases, human-occupied submersibles carrying scientists directly to the deep allow for unparalleled real-time observation and sampling, providing a direct, immersive experience of these submerged historical sites. The scientific study of wreck sites extends far beyond mere identification. Maritime archaeology treats wrecks as invaluable time capsules, offering unparalleled insights into past cultures, technologies, trade routes, and daily life at sea. The artifacts, recovered ceramics, tools, personal belongings, cargo, provide tangible connections to the people who sailed these vessels, offering a glimpse into their world. The construction techniques of the hull, the design of the rigging, the type of engine all speak volumes about the technological capabilities of their era. Forensic oceanography analyzes the physical state of the wreck and its debris field to reconstruct the events of its loss. Was the vessel intact when it sank, suggesting a gradual flooding or capsizing? Or was it violently torn apart, indicating a catastrophic structural failure, an explosion, or an extreme weather event? The distribution of debris, the nature of the impact marks on the sea floor, and the degree of fragmentation all provide crucial clues. For aircraft wrecks, the pattern of engine components, fuselage parts, and wings can indicate whether the aircraft broke up in the air or upon impact with the water. This meticulous scientific detective work transforms a tragic incident into a rich source of data, helping engineers design safer vessels and providing critical information for maritime accident investigations. Wreck sites also become artificial reefs, attracting and supporting diverse marine life. Over time, corals, sponges, and other sessile organisms colonize the hard surfaces of the wreck, transforming it into a vibrant, if temporary, oasis in the deep. Fish and other mobile creatures seek shelter and food among the structures, creating unique ecosystems that are themselves subjects of biological study. However, wrecks can also pose environmental hazards, slowly releasing pollutants such as fuel oil lubricants and hazardous cargo, which can impact the surrounding marine environment. Scientists monitor these sites to assess and mitigate potential long-term ecological consequences. The Bermuda Triangle, with its long history of maritime activity, its proximity to major shipping lanes, and its susceptibility to powerful storms, naturally contains a significant number of wrecks. These silent sentinels, far from perpetuating a sense of inexplicable mystery, offer tangible scientific evidence of the ocean's immense power and the enduring legacy of human exploration. Each discovered wreck, meticulously documented and studied, adds another layer to our understanding of this dynamic region, transforming whispers of legend into the clear, resonant voice of scientific discovery. As you drift deeper into the quietude of your own sleep, let the image of these silent, submerged archives, patiently awaiting their stories to be told, fill your mind with a sense of profound peace and the boundless richness of our shared history beneath the waves. Mapping the unseen, the science of deep-sea bathymetry. From the silent sentinels, the scattered remains of human endeavor, resting in the profound stillness of the deep, we now cast our gaze across the entire vast expanse of the ocean floor itself. For before we can truly understand the secrets held within its sediments or the life that thrives in its darkness, we must first learn to map the unseen, to reveal the intricate topography of this hidden world. This is the science of deep-sea bathymetry, the meticulous art and rigorous science of measuring ocean depths and charting the contours of the submarine landscape, a patient endeavor that transforms the featureless blue into a richly detailed, three-dimensional reality. For centuries, the only way to gauge the ocean's depth was through the laborious tactile method of sounding lines. Imagine a heavy lead weight, often conical, attached to a long, carefully marked rope or chain. This lead line would be slowly, painstakingly lowered over the side of a ship, feeling its way down through the water column. The mariner would watch the line unspool, counting the markers as it descended, until a faint, muffled thud indicated that the weight had gently touched the seabed. A small hollow in the base of the lead, often filled with tallow or wax, would collect a sample of the bottom sediment, a tangible, if crude, piece of information about the seafloor's composition. This method, while direct, was incredibly slow, providing only a single-point measurement at a time. To map even a small area would require countless soundings, a painstaking manual process that left vast stretches of the deep ocean entirely unknown, a blank canvas beneath the waves. The true revolution in bathymetry began with the advent of acoustics in the early 20th century. The principle was elegantly simple sound travels through water. The single-beam echo sounder, or photometer, became the mariner's new eye into the deep. Picture a transducer mounted on the ship's hull, emitting a sharp, focused pulse of sound, a solitary ping, directly downwards into the water. This sound wave travels through the water column, bounces off the seafloor, and returns as an echo to a receiver on the ship. By precisely measuring the time it takes for the sound pulse to make this round trip, and knowing the speed of sound in water, the depth can be accurately calculated. It was a monumental leap forward, allowing ships to continuously measure depth as they moved, drawing a single narrow profile of the seafloor directly beneath their keel. This technology transformed navigation, allowing ships to avoid shallow hazards, but still left the vast areas to either side of the ship's track shrouded in mystery. The true unveiling of the unseen landscape, however, came with the development of multi-beam echo sounders, MBES. This technology, emerging from the mid-20th century and continuously refined, is the cornerstone of modern deep-sea mapping. Instead of a single narrow beam, a multi-beam system employs an array of transducers that simultaneously emit a fan of hundreds of individual narrow sound beams, sweeping across a wide swath of the seafloor. Imagine a colossal, invisible broom sweeping across the seabed, painting a detailed picture with sound. Each of these hundreds of beams measures the depth at a slightly different angle and position, and when all these individual depth measurements are combined, they create a continuous high-resolution strip of bathymetric data, often covering an area several times wider than the depth of the water itself. The process is intricate and demanding. As the research vessel slowly glides across the ocean surface, the multi-beam system continuously pings, sending out its fan of sound. The echoes from each beam return are precisely timed and then meticulously processed. This processing involves correcting for the ship's motion, its roll pitch, and yaw, which are measured by sophisticated inertial navigation systems. Crucially, the speed of sound in water is not constant. It varies with temperature, salinity, and pressure. Therefore, CTD, conductivity temperature. Depth sensors are deployed regularly to measure these parameters throughout the water column, allowing for precise corrections to be applied to the sound travel times. The resulting data points, millions upon millions of them, are then compiled into vast digital datasets, which can be rendered into stunningly detailed three-dimensional maps of the ocean floor, revealing every ridge, valley, seamount, and canyon with astonishing clarity. This is how we come to visualize the intricate geological architecture of regions like the Bermuda Triangle. Beyond direct acoustic sounding, another powerful technique for mapping the unseen, particularly for large-scale features, comes from space satellite altimetry. Imagine satellites orbiting thousands of kilometers above the Earth, continuously emitting radar pulses that bounce off the ocean surface and return. By precisely measuring the time it takes for these pulses to return, scientists can determine the exact height of the sea surface. Now here is the profound insight, the very skin of the ocean. A fluid membrane subtly rises and falls in response to minute variations in Earth's gravity. denser features on the seafloor, such as massive seamounts or thick sections of oceanic crust, exert a slightly stronger gravitational pull, subtly attracting the water above them, causing a tiny bulge on the sea surface, perhaps only a few centimeters high. Conversely, deep ocean trenches, being regions of mass deficit, create slight depressions in the sea surface. By meticulously measuring these tiny variations in sea surface height, scientists can infer the underlying topography of the seafloor, even in areas that have never been directly surveyed by ships. Satellite altimetry provides a global coarse resolution map of the ocean floor, revealing vast, previously unknown mountain ranges and fracture zones, a silent echo of the deep geology imprinted on the ocean's skin. For exceptionally high resolution mapping of specific localized areas such as a wreck site or a hydrothermal vent field, autonomous underwater vehicles, AUVs, and remotely operated vehicles, ROVs, are indispensable. These unmanned submersibles can carry specialized high-frequency sonar systems much closer to the sea floor than a surface vessel ever could. By operating just tens of meters above the bottom, they can collect bathymetric data with centimeter-scale precision, revealing minute details: the individual planks of a sunken ship, the precise contours of a deep-sea coral mound, or the subtle ripples in the sediment. Imagine these silent, robotic explorers gliding slowly through the eternal darkness, their sonar eyes painting an incredibly fine-grained portrait of the immediate seabed, uncovering secrets that even multi-beam sonars from the surface cannot resolve. Once the vast quantities of bathymetric data are collected, they undergo rigorous processing and visualization. Sophisticated computer software corrects for all known errors and integrates the millions of individual depth points. The results are then used to create detailed bathymetric charts, which are essentially topographic maps of the ocean floor. These charts utilize contour lines to depict areas of equal depth, much like contour lines on a terrestrial map show elevation. They are often color-coded with blues and purples, representing the deepest areas, and greens and yellows, indicating shallower regions. These visualizations allow oceanographers, geologists, and biologists to see the unseen, to study the intricate morphology of the seafloor, and to understand its profound influence on oceanographic processes. The intricate bathymetry of the Bermuda Triangle region, painstakingly mapped over decades of scientific expeditions, reveals the very features we have discussed in previous chapters. The gradual slope of the continental shelf and the dramatic plunge of the continental slope off Florida are clearly delineated. The vast flat expanse of the abyssal plains is revealed, punctuated by the majestic rise of the Bermuda seamount. The colossal deep scar of the Puerto Rico Trench, with its incredibly steep walls and profound depths, is meticulously charted its contours, speaking of immense tectonic forces. The subtle undulations of the Blake Ridge, a massive sediment drift, become visible, revealing the slow work of currents and deposition. This detailed understanding of bathymetry is not merely an academic exercise. It is fundamental to countless aspects of ocean science and human activity. It is essential for safe navigation, providing mariners with accurate charts to avoid submerged hazards. It is critical for understanding ocean currents, as the topography of the seafloor profoundly influences their flow patterns. It helps geologists study plate tectonics, revealing the structure of mid-ocean ridges, fracture zones, and subduction trenches. It is vital for marine biology, as seafloor features create diverse habitats, influencing the distribution and abundance of marine life. It aids in the search for natural resources such as methane hydrates or mineral deposits. And as we explored, it is an indispensable tool in search and recovery efforts, allowing researchers to systematically search for lost ships, and aircraft transforming vast, empty spaces into scientifically manageable search grids. Despite these astonishing technological advancements, it is important to remember that much of the deep ocean floor remains unmapped at high resolution. Vast areas have only been surveyed by satellite altimetry, providing a blurry, generalized view. The quest to map the entire global ocean at resolutions comparable to terrestrial landscapes is an ongoing, monumental endeavor, a testament to humanity's enduring curiosity about our own planet. Each new survey, each new ping of sound, peels back another layer of the unseen, revealing more of the silent, enduring secrets cradled beneath the waves. As you drift deeper into the quietude of your own sleep, let the image of these invisible sound waves gently painting the hidden contours of the deep fill your mind with a sense of profound peace. Imagine the vast, unseen landscapes slowly, patiently revealing themselves, turning the unknown into the gently understood. Allow the quiet hum of scientific discovery to lull you, a slow, continuous unfolding of knowledge, carrying you softly into a peaceful, dream-filled ocean. The unannounced discoveries. Unveiling data from oceanographic expeditions. The meticulously charted contours of the deep, unveiled by the patient science of bathymetry, are not merely lines on a map. They are the canvas upon which countless other, often subtle discoveries have been painted by the tireless work of oceanographic expeditions. These are the unannounced discoveries, not in the sense of being deliberately hidden, but rather as the quiet, incremental advancements of knowledge. The detailed findings that gradually build a more complete, nuanced portrait of our ocean, often shared within specialized scientific communities rather than through dramatic public pronouncements. Imagine the specialized research vessels, sleek and silent, gliding across the surface of the Bermuda Triangle region, their hulls bristling with an array of sophisticated sensors. Aboard these floating laboratories, scientists from institutions like the National Oceanic and Atmospheric Administration, NOAA, various university marine science departments and international research collaborations patiently gather data day after day, year after year. Their missions are not to chase fleeting rumors or sensational mysteries, but to systematically probe the ocean's physical properties, its geological underpinnings, its chemical composition, and the astonishing biodiversity it cradles. Each expedition returns with vast quantities of raw data, a treasure trove of information that, once meticulously processed and analyzed, unveils a multitude of findings that deepen our scientific understanding. Consider, for instance, the fine-scale bathymetry that continues to be refined through high-resolution multi-beam surveys. While we have discussed the grand features, these detailed maps often reveal previously unknown microtopographic features. Imagine a sudden sharp ridge, perhaps only a few hundred meters long and tens of meters high, emerging from an otherwise flat abyssal plain. Or a series of subtle linear depressions too small to be detected by satellite altimetry that mark ancient inactive fault lines in the oceanic crust. These minute features, though seemingly insignificant, can profoundly influence localized deep-sea currents, create unique habitats for benthic organisms, or offer subtle clues about past geological stresses and volcanic activity that are not evident from larger-scale mapping. The discovery of these intricate small-scale structures is a constant, ongoing process, gradually filling in the blank spaces of our deep-sea charts with astonishing detail, transforming a generalized understanding into a finely wrought blueprint. The dynamic nature of ocean currents far beyond the broad strokes of the Gulf Stream has also been a subject of extensive unannounced discovery. Long-term deployments of mooring arrays, where a series of sensors are anchored to the seafloor and stretch up through the water column, have patiently recorded current velocities, temperatures and salinities at various depths, sometimes for years on end. The data from these silent sentinels reveal the complex multi-layered structure of deep-sea flows, uncovering the existence of internal waves, vast, slow-moving waves that propagate within the water column rather than on the surface, and the intricate fine structure of mesoscale eddies that spin off the main currents. These findings, published in specialized oceanographic journals, detail how these localized currents influence the transport of sediment, the distribution of nutrients in the deep, and even the dispersal patterns of larval marine life, painting a picture of an ocean far more turbulent and dynamic beneath the surface than once imagined. Furthermore, the study of methane hydrates has moved far beyond simple detection. Oceanographic expeditions have deployed sophisticated instruments to directly sample and monitor these frozen fire deposits. Deep-sea drilling programs have extracted long cores of sediment, bringing up samples of hydrates that are then analyzed in specialized pressure laboratories on board research vessels. These analyses reveal the precise chemical composition of the methane, helping scientists differentiate between biogenic and thermogenic sources, and providing insights into the microbial communities that generate or consume methane within the sediments. High-resolution seismic surveys combined with direct observations from ROVs, remotely operated vehicles, have also unveiled the morphology of specific hydrate mounds, identified active cold seeps, where methaneric fluids bubble from the seafloor, and mapped the distribution of pockmarked circular depressions on the seabed that signify past gas expulsion events. These detailed findings, often focused on specific sites like the Blake Ridge, contribute to a global understanding of the methane hydrate reservoir, its stability, and its potential role in the carbon cycle, far from any dramatic claims of exploding ships. The abyssal realms of the Bermuda Triangle, including the profound depths of the Puerto Rico Trench, continue to yield a steady stream of new species discoveries. Each deep-sea submersible dive, or ROV deployment, each carefully executed deep-sea trawl, often brings to light organisms previously unknown to science. Imagine a delicate, translucent sea cucumber, its body adapted to the crushing pressure, slowly feeding on marine snow on an abyssal plain that has never before been observed. Or a unique species of bioluminescent fish, its light organs configured in a pattern never before seen, discovered in the dark, cold waters of the trench. These discoveries, often painstaking to classify and describe, are published in taxonomic journals, adding incrementally to the global catalogue of biodiversity and revealing the astonishing adaptability of life in extreme environments. They are not often celebrated on evening news, yet each new species is a profound testament to the ocean's biological richness and the vastness of our unexplored world. Sediment core analysis provides another rich vein of unannounced discoveries. Scientists extract long cylindrical cores of sediment from the seafloor, sometimes extending dozens of meters into the past, representing millions of years of deposition. Each layer within these cores is a silent archive. By analyzing the fossilized remains of microscopic organisms, foraminifera, diatoms, radiolarians, the chemical composition of the sediment, and the presence of specific mineral grains, scientists can reconstruct detailed paleoclimate records. They can identify periods of past ocean warming or cooling track changes in ocean currents, reconstruct the history of major dust storms from distant continents, and even find evidence of ancient hurricane activity, preserved as layers of coarse, storm-deposited sands. These subtle, nuanced findings, often requiring years of laboratory analysis, contribute to our understanding of long-term climate variability and the ocean's response to environmental change, far more impactful than any single dramatic discovery. Furthermore, geophysical surveys continue to refine our understanding of the deeper crustal structure. Detailed magnetic anomaly maps, far more precise than historical charts, unveil the intricate patterns of seafloor spreading, revealing subtle bends and offsets in ancient fracture zones that speak to the complex history of plate movements. Gravity anomaly surveys detect variations in the Earth's gravitational field, which can indicate the presence of denser or less dense rock formations deep beneath the seafloor, helping geologists infer the composition and structure of the crust and upper mantle. Seismic reflection and refraction profiles using powerful sound waves to penetrate deep into the Earth's crust reveal the complex layering of sedimentary basins, the architecture of fault systems, and the precise geometry of the subducting plate in the Puerto Rico Trench. These are the tools that allow scientists to see thousands of meters into the Earth, transforming abstract geological theories into concrete, data-driven models, gradually building a comprehensive understanding of the deep Earth processes at play in this region. Even the study of wreck sites, while sometimes captivating to the public, yields a wealth of unannounced scientific data. Maritime archaeologists and forensic oceanographers meticulously document debris fields using ROVs to map every scattered fragment. This detailed mapping allows them to reconstruct the sequence of events leading to a vessel's loss, with scientific precision identifying points of structural failure, the likely impact forces, and the influence of currents on debris dispersal. These analyses contribute to naval architecture, marine engineering, and safety protocols, providing practical, data-driven insights far removed from sensationalized tales. The long-term biological colonization of wrecks also provides valuable data for marine ecologists, studying how these artificial structures become habitats and how deep-sea communities adapt to and utilize them over decades and centuries. The beauty of these unannounced discoveries lies in their cumulative power. No single finding may shatter preconceived notions in a dramatic flourish, but each data point, each peer-reviewed paper, each new map or species description slowly, patiently, and rigorously builds a more accurate, scientifically robust understanding of the Bermuda Triangle region. It is a testament to the scientific method, the formulation of hypotheses, the meticulous collection of data through expeditions, the rigorous analysis, and the careful dissemination of findings within the global research community. These are not secrets kept from the public, but rather the quiet, persistent pulse of scientific progress, transforming the unknown into the gently understood piece by painstaking piece. As you drift deeper into the quietude of your own sleep, let the image of these silent research vessels patiently gathering data from the dark, cold depths fill your mind with a sense of profound peace. Imagine the countless scientists poring over maps and graphs, slowly, methodically unveiling the intricate factual wonders of our ocean. Allow the gentle hum of continuous discovery to lull you, a slow, continuous unfolding of knowledge, carrying you softly into a peaceful, dream-filled ocean where every whisper of data adds to the grand, quiet story of our world. The ocean's unending story, drifting towards new horizons of knowledge. The ceaseless, unannounced discoveries patiently gathered from oceanographic expeditions across the Bermuda Triangle region have illuminated its geological foundations, traced its invisible currents, revealed the sky's profound influence, mapped its magnetic whispers, probed the secrets of its frozen fire, and unveiled life flourishing in its perpetual night. We have meticulously charted its unseen bathymetry and painstakingly analyzed the silent sentinels of its wreck sites. Yet despite this wealth of knowledge, the ocean's story, particularly in these deep, remote expanses, is far from fully told. It is an unending narrative, perpetually drifting towards new horizons of knowledge, beckoning with more questions than answers. Consider the sheer staggering scale of the unknown. While advanced multibeam sonar has mapped significant portions of the global ocean floor, vast areas, particularly in the deep abyssal plains and the profound depths of the Hadal trenches, remain unmapped at high resolution. Imagine immense sprawling valleys, towering submarine mountains, and intricate geological formations that have never been seen by human or robotic eyes, their contours only vaguely inferred from satellite altimetry. These unexplored landscapes undoubtedly hold undiscovered species, unique ecosystems, and untold geological secrets waiting patiently in the eternal darkness for the silent gaze of scientific inquiry. The challenges to unveiling these remaining mysteries are formidable, rooted in the very nature of the deep ocean environment. The immense pressure, increasing relentlessly with every meter of descent, demands incredibly robust and specialized equipment, capable of withstanding forces that would crush conventional materials. The perpetual darkness necessitates powerful, energy-intensive lighting systems for any visual observation, and the cold, near-freezing temperatures stress electronics and batteries, limiting the operational endurance of autonomous vehicles. The sheer remoteness of these deep-sea environments means that every expedition is a monumental logistical undertaking, requiring specialized ships, extensive scientific teams, and significant financial investment making. Exploration a slow, deliberate, and costly endeavor. Despite these challenges, the scientific community is continuously pushing the boundaries of technology and methodology, developing innovative approaches to pierce the ocean's veil. The next generation of autonomous underwater vehicles, AUVs, and remotely operated vehicles, ROVs, are at the forefront of this advance. Imagine AUVs capable of even greater autonomy, programmed with sophisticated artificial intelligence that allows them to make real-time decisions, adapt their survey patterns based on incoming data, and operate for weeks or even months without human intervention. These intelligent explorers will carry an expanded suite of advanced sensors, including high-resolution chemical sniffers to detect subtle plumes from cold seeps, acoustic cameras to see through murky waters, and advanced biological sensors to identify genetic material from unknown organisms. The concept of swarm robotics, where multiple AUVs work collaboratively, communicating with each other to cover vast areas more efficiently and simultaneously, gather diverse datasets, is also rapidly developing, promising to accelerate the pace of deep-sea discovery. Beyond individual vehicles, the establishment of deep-sea observatories represents another crucial horizon. Imagine permanent cabled installations anchored to the seafloor, continuously streaming real-time data back to shore for years on end. These observatories, equipped with an array of sensors, seismometers to monitor tectonic activity, hydrophones to listen for deep-sea sounds, current meters to track subtle flows, chemical sensors to detect methane and hydrogen sulfide, and cameras to observe biological activity, provide an unprecedented long-term perspective on deep-sea processes. Such continuous monitoring allows scientists to capture rare episodic events like submarine landslides or sudden methane releases that might be missed by fleeting expeditions, offering a deeper understanding of the ocean's dynamic long-term rhythms. The field of genomics and molecular biology is poised to revolutionize our understanding of deep-sea life. By analyzing environmental DNA, tiny fragments of genetic material shed by organisms into the water, scientists can detect the presence of species, including those that are rare, elusive, or yet to be discovered without ever having to physically capture them. Imagine a single water sample revealing the genetic signatures of dozens of unknown deep-sea fish invertebrates and microbial communities, painting a rich picture of biodiversity that traditional methods could never achieve. Furthermore, the study of extremophiles organisms adapted to extreme conditions at the molecular level will continue to reveal fundamental insights into the very limits of life, potentially offering clues to the origins of life on Earth and the possibility of life on other celestial bodies. The integration of vast datasets through artificial intelligence (AI) and machine learning will transform how we analyze and interpret the ocean's unending story. Imagine AI algorithms sifting through petabytes of sonar data, identifying subtle patterns in bathymetry that human eyes might miss, or analyzing millions of deep-sea images to automatically classify species and track their behaviors. Machine learning models can be trained to predict the occurrence of deep-sea hazards, the stability of methane hydrate deposits, or the long-term impacts of climate change on abyssal ecosystems, extracting profound insights from the overwhelming volume of data collected by modern oceanography. Finally, the future of ocean exploration, particularly in regions as complex as the Bermuda Triangle, lies in increasingly interdisciplinary collaboration. Geologists, oceanographers, biologists, chemists, engineers, and computer scientists must work together, sharing their specialized knowledge and integrating their data to construct a truly holistic understanding of these intricate environments. The story of the ocean is not told in isolated chapters, but in the seamless, interwoven narrative of its physical, chemical, and biological processes. Understanding the deep ocean, even in specific regions like the Bermuda Triangle, extends far beyond mere scientific curiosity. It is intrinsically linked to some of the most pressing global challenges of our time. The deep ocean plays a critical role in global climate regulation, acting as a vast reservoir for heat and carbon dioxide. Understanding deep-sea currents and the stability of methane hydrates, therefore, directly informs our knowledge of climate change and its potential impacts. The deep sea harbors immense biodiversity, much of it still unknown, and its preservation is crucial for the health of the entire planet. As human activities such as deep-sea mining or fishing expand into these realms, scientific knowledge becomes paramount for responsible stewardship and conservation. The very processes of plate tectonics, seismic activity, and submarine landslides studied in detail in regions like the Puerto Rico Trench contribute to our understanding of natural hazards and planetary evolution. The Bermuda Triangle, with its rich tapestry of geological features, dynamic currents, and unique life forms, therefore remains a vibrant, active frontier for scientific exploration. It is a place where every new expedition, every new sensor deployment, every new data point peels back another layer of the unseen, transforming perceived enigma into tangible, verifiable knowledge. The whispers of old legends fade, replaced by the resonant, data-driven voice of scientific discovery. The ocean story is continuous and endless unfolding of wonders, with each new horizon of knowledge revealing more of the profound, quiet truths that lie beneath the waves, inviting persistent, gentle inquiry. And so, as we drift away from the scientific whispers of the deep Atlantic, from the hidden landscapes and unseen flows of the Bermuda Triangle region, our journey into its depths now gently recedes, much like the ebbing tide softly withdrawing from the shore, or the sun's slow descent beyond the horizon, inviting the quietude of night. Through the patient gaze of science, the perceived enigmas of this oceanic expanse have softened into comprehensible patterns, much like the gentle unraveling of complex thoughts as you surrender to slumber. The slow, methodical unveiling of data, of currents, and geology of life flourishing in the dark can guide your own mind towards a similar clarity. a peaceful processing of the day's journey. Let the vastness of the ocean's observed truths, the steady rhythm of its scientific pulse quiet any lingering restlessness. May the deep, quiet certainty of scientific understanding settle softly upon your consciousness, and the gentle, rhythmic pulse of the ocean's vast currents lull you into a profound and dream-filled rest. Sleep well. See you again.